sick at the minute. My name's Seb. I'm just coming to the end of my PhD and Ivan supervises me. Ivan does a lot of deep sea stuff, sea level rise, ocean currents, etc., whereas my bag is beaches and coasts. So I did an undergrad and a master's at Plymouth on exactly this. My PhD at Southampton now is on rip currents, which we'll learn about in a moment. What you would have gone on to do today and in the coming lectures with Ivan is tides, waves, and sea level rise. Now, has anyone studied waves in terms of nearshore waves before? Just show of hands? Not at all. Okay. We'll come to that slightly. I won't steal Ivan's thunder too much, but we'll discuss waves in a small bit of depth here, and you'll get the full lecture when he's back off sick. In terms of what we're going to look at today, it's just a total introduction then to morphology, controls, and nearshore processes on beaches and barriers. The outcomes then, the first thing is to look at different morphological features on beaches and barriers, such as berms, bars, the swash zone. We'll then look at what controls those features. So you go to a beach day in, day out, and you see a change. Why is that change in place, and what influences that change? We'll look at the three main sets of nearshore currents. So there's a longshore current that if you've done geography at A-level, you've studied to death. Bed return flow, and like I said, rip currents. And then we'll look at how we can predict shoreline change under changing sea levels. So one of your lectures to come is on sea level rise, and this will give you a little bit of an insight into how sea level rise might affect the coastline as we know it. So why are beaches important? The first reason is coastal protection and resilience. Does anyone know what that picture is of? In terms of the scenario? Any ideas at all? Dawlish, good. Okay, so 2014, the 5th of February 2014, there was a huge set of storms that hit the coastline of the UK, more so around the southwest. That train line that you see is the main commuter route that connects the southwest, anywhere southwest of Exeter, to the rest of the country. And the train line was knocked out for 2 months, okay, as a result of that. The impact was millions, if not billions, in terms of lost economy. The actual cost of repair to that train line was £35 million over a period of 2 months, where the southwest was effectively disconnected from the rest of England. So beaches are important for coastal protection. There used to be a beach in front of the seawall that you can see there, but that series of storms eroded it to the point where it then eroded the seawall and eventually the train line itself. They also create unique environments. This is again on the southwest coast. That's the largest freshwater reservoir in southern England. And if you're into your plants and bits and bobs, there is a medicinal plant that grows on the back of that barrier. It's the only place in the UK that it grows, and I'm led to believe it's used widely in medicine around the UK. Okay? It's only there because of that natural mix between the seawater on one side, the fresh water, and the mixing between the two. But perhaps our best known reason to use the coast and why they're important is recreation. Over 50% of the UK go to the beach for a day out each year. Okay, you might think it would be more, unfortunately it's not. Recreation brings in hundreds and hundreds of pounds, millions and millions of pounds to our economy each year. And you would have touched on coastal ecosystem services in your last lecture with Ivan. So you already know about the economy in terms of what we can bring in. An overview of this lecture then. We're going to touch on shore face morphology, and we'll define the shore face, okay, as opposed to the wider coastal zone that we spoke with Ivan about in the last lecture. As I said, we're going to look at the controls on beach morphodynamics, but also different beach types and how they vary in between states. And we'll then look at barriers. Barriers are slightly different beasts to beaches themselves, and finally we'll look at how those barriers respond to changing sea levels. Starting with the definition then, a beach is first of all a collection of wave-deposited sediment. Some of the other lectures you're going to have with Ivan will touch on estuaries. Okay, estuaries are generally tide-deposited sediment. So there's a lot longer settling time. The water motions are a lot smoother and therefore finer sediments fall out of suspension and form that estuarine mud that you kind of know. You won't find a muddy, in the sediment size definition terms, beach, because it's wave deposited. There's too much energy in waves to deposit that fine mud and silt. As beaches accumulate then under calm conditions, more and more sediment gets pushed on shore. Okay? They build a larger feature that's no longer subject to wave action, and that's the barrier. Okay? So you can think of going to the beach and you can watch the tide come in and out, and during that course of the day, perhaps 60% of the beach will be subject to wave action as a result of the tide. We can think of the beach as being on the larger feature, which is the barrier. There's 40% of that feature that will not get affected by the waves 90% of the time, 95% of the time. That's the stable feature that doesn't move. The beach is the dynamic feature that changes as a result of waves and tides. Okay, so that's the subtle difference between the two. Barriers generally then are large shore parallel accumulations of sediment, and as we've touched on, they're formed over longer time scales. So we talk about barrier change, and we'll touch on that at the end of this lecture. When we talk about barrier change, we're talking over 5s, 10s, 50s of years, as opposed to the beach, which we talk about changing on this seasonal or even this weekly time scale. So the beach, to take away from this then, is the active part. The barrier is that stable platform on which you see the beach itself. In terms of sediment size, we get two types of beach, gravel and sand. Okay, there is a scale of sediment size, which I'm sure you've seen or you will see soon in your lectures. Gravel beaches are generally steeper. Okay, the reason being, as gravel sticks together, there are a lot more holes between sediment particles, and as the waves push the gravel onto the beach, that water seeps through the gravel, through all those pores, and drains away at a lower level. Therefore, there's no backwash action to take the gravel back offshore. So it's only affected by the swash up the beach, which piles it up. As opposed to sand, when sand groups together, there's far less air and gaps between sediment particles, and therefore the water swashes up the beach. It can't drain through the sand, so it takes the sand back down. And as a result of those two processes, that infiltration in the gravel, you'll see that gravel beaches are very often steeper than their sandy counterparts. I've already said that mud and silt doesn't form beaches because it's too fine for that wave deposition. It goes back to the settling time that I touched on a moment ago. In wave action, it's quite fierce and quite energetic. The sediment will never fall out of suspension if it's that sort of size. So you only really find sand and gravel beaches. Occasionally, higher than that, you find boulder beaches, which you can see at the top of the scale there. In terms of features of the beach then, the main zone we're going to focus on is the shore face. Okay, the definition I'm going to give you for the shore face is it starts down here at the wave base. Okay, this is the point at which waves start to interact with the seafloor. So as waves propagate over open ocean, there's no interaction with the seabed. But it comes a point, as they get into shallower and shallower water, where the bottom of that wave base touches, or starts to interact, starts to experience friction with the seabed. That's the wave base, that's our offshore extent of the shore face. Our onshore extent of the shore face is defined by the swash zone. So as a wave breaks, you get a breaking motion, and then you get a rush up the beach of a thin lens of water. We define the edge of our shore face by the extent that that lens of water reaches up. So picture yourself on the beach, see the waves breaking, that uprush of water, as far as that gets, we define as the limit of the shore face in terms of the landward extent. What we're going to do now then, just beyond that, we go into aeolian-type features such as dunes. Okay, so we wouldn't classify those sorts of features, again formed over longer time scales, as part of the shore face. So swash to wave base. If we now take the offshore limit, so again, here we've got the wave base, we talk about a wave shoaling zone. Now, in terms of waves interacting with the seafloor, again you'll learn this slightly more with Ivan. As a wave propagates across the ocean, the orbit of the actual particles in the wave is circular. So there's no net movement of water particles as a wave propagates. Instead, there's a net movement of energy. Think of Newton's cradle. As the particles hit each other, they pass the energy on, but they don't actually move themselves. And the same is true as waves propagate. If you picture yourself bobbing around in the surf zone, as a wave comes by, it will pick you up, it might move you forward, but straight away you'll feel a motion that sort of drops you and moves you back. And that's this circular orbit that you can see. Near the surface we get big orbits, but as we get lower and lower, as the wave to the bottom of the wave height, to the trough of that wave, the orbits become smaller. And in open ocean, when those waves aren't shoaling, those orbits are perfectly circular, because there's no interaction with the seabed, there's no friction, and therefore those orbits just carry on as such. When we get to this wave base, this is also termed the depth of closure, so there's two terms for it. The bottom of that wave base starts to interact with the seabed. It starts to slow the wave down, and because the wave is slowing down, all the waves behind it, still going at faster speed, catch up with it, and that's why you see waves shoal. So if you look out to sea from a beach, out 300 or 400 metres, you'll see a largely flat surface. But as you look in towards the shore, you'll start to see the mounds of the waves. As you look closer to shore, you'll see the waves breaking. That's the process of shoaling. And what happens is the wave base here touches the seafloor. We get that interaction, that friction, the wave slows down, and rather than these perfectly circular orbits, what you can see on there is the orbits become squashed. Okay? And as we go further and further onshore to here, they're almost lateral backwards and forwards as a result of that interaction with the seabed. So when we talk about the shoaling zone, this is the region whereby the waves are interacting with the seabed. That's the definition you need for the shoaling zone. And it starts at that depth of closure, which is that influence on the seabed. You can see that change in orbital pattern. And this depth of closure is the seaward limit of significant, and that's important, significant cross-shore sediment transport. Because offshore of that, there's no interaction with the seabed. So there's no means to entrain sediment to move it onshore until the waves are interacting. So shoaling zone then starts at that depth of closure, and it moves onshore. This is a picture exactly as I explained. Offshore you see largely flat, then you start to see the mounding of the waves, and inshore you'll start to see them breaking. And we'll look at the breaking processes in a moment. So wave breaking then. The zone in which the waves break we call the surf zone. So you've gone from the shoaling zone to the surf zone. On a lot of beaches you get a feature called a bar, and this is an offshore feature. It's an accumulation of sediment, and therefore it's shallower in water depth than the areas surrounding it. As the waves approach the bar, because there's a sudden change in depth, that wave is now interacting with the bar in a much greater way. There's a lot more friction, it slows down tremendously. Certainly the base of the wave slows down, but the top of the wave carries on at the same speed, and that's what induces breaking. You can imagine the bottom of the wave slowing down, the top of the wave going at the same speed, and we get to a point where it can't sustain itself, and effectively the top of the wave falls over. That's what induces breaking in waves at the beach. A feature like a bar can induce that, because that rapid change in depth is too much for the wave to handle. We define a bar as a collection of sediment. Okay? It's formed by sediment convergence, and if we look at that top diagram, from the beach we get some form of almost erosion back down, and here, from that depth of closure, we get onshore transport. And where those two meet, we get that accumulation of sediment. That's the offshore bar. And you can see that sometimes we get multiple bars on beaches as a result of different wave heights, different tidal levels, different interaction processes. And in the middle we see troughs or channels. Okay? And we'll come back to the channels later on because they're a key driver of rip currents. So the surf zone then is where those waves start to break. And again, that's a gap in the channel. So what you see here is a time-lapse image. This is an image taken over 10 minutes. Where the waves are breaking, we can see a blurred white line. Okay? You can see just down here that we have a darker region. That's the landward extent of the bar. And in the middle, you get a gap here. That's a channel through the bar. Okay, so we've gone from shoaling to breaking and now into swash. The swash zone is that upper part of the beach that's intermittently wet and dry on the timescales of breaking waves. So this is that thin lens that I spoke about. As the waves crash down onto the beach, they form a surge of water that runs up the beach and runs down. That surge of water up and down is swash. So the swash zone, the upper extent is defined by the landward limit that swash lens reaches. So how far up the beach does that swash go? We call it swash. What we also hear it referred to is uprush and backwash, which are the onshore and offshore flows respectively. The onshore flow is driven by the momentum of the waves. The backwash is driven by gravity. Generally, you can picture the beach has generally got an angle, okay, and gravity-driven flows drive that backwash down the beach. If we look at the beach face itself, so we've now got two similar terms. We've got the wider term, which is the shore face, and within that we have a small region which we refer to as the beach face. This is the planar, as in linear, relatively steep upper part of the beach profile subject to swash. And here you can see that as the dashed line. What I've tried to highlight is there is a break in profile about there. Okay? That's a slightly different feature. The beach face itself is that largely linear area that's subject to swash. Along here, you can see a change in colour. Straight away that tells you where the swash is finishing. However, at higher tidal levels, you'll see that swash impacts up here. So that's the beach face. We could also talk about the shoreline. Now the shoreline is very, in simple terms, is again planar. It's the part subject to swash, so we're talking about an area on the beach face, but it's that physical interaction between water and sand. So this is the delineation between the sea and the land, and we refer to that as the shoreline. And obviously, that changes as we progress through the tide, like so. Okay, at the top of the beach face, under calm conditions, we may get a feature that we refer to as the berm. Okay? The berm is another planar section, but it's landward of the beach face. So what you can imagine has happened here is calm conditions have driven sediment onshore. That swash is eroding some of the sediment slightly, which is why you get this beach face here. Okay? And what's left, what's accumulated, is into this berm-like feature. So often you'll see it as a mound on the beach, and you will always see a break point here, which we refer to as the berm crest. So that berm crest is the point between the berm and the beach face itself. You can see in the diagram on the left, just an idealisation of that. So you get a steep beach face that's accumulated all this sediment. You get the berm crest, and then on the back you get the berm itself. What we're going to look at then is the seasonal control on those features, specifically bars and berms. We talk about a summer profile, and in the literature you'll also see it referred to as a swell profile. This is formed in calm conditions where there's low wave steepness, i.e. the wave height is small compared to the wave length. That's a low steepness condition. And it's conducive to onshore transport. So the calm conditions are what you see build up the beach. They're also responsible for the creation of that berm feature. Don't need to worry too much about this, but you can see swell profiles and storm profiles are governed by a number of things. The first of which is wave steepness, so the ratio between height and length of the waves, but they're also governed by the grain size. As I said earlier, gravel beaches will form much steeper beaches than sand. What you do need to have a look at, though, is how that berm changes as we go from summer or swell conditions to winter or storm conditions. So here we have the high tide level. Above that, we have the berm feature. It's above the high tide level, because if you imagine at high tide, there are waves breaking on the beach, and that swash lens comes up over the berm itself. So the berm will always be above high tide level. It's an accumulation of sediment as a result of onshore transport. As we switch to a winter storm profile, where the conditions are now energetic, there's a high wave steepness, as in the wave height is large compared to the wave length. We get erosion, and all that sediment from the beach moves offshore, it goes below the waterline, and it forms sandbars or offshore bars. And as I said earlier, you can have 1, 2, 3, multiple bars in some scenarios. So that winter or storm profile is characterised by beach erosion and net offshore transport. And it is a seasonal control, because generally you'll see that through the summer months there is a lot more sediment on the beach. You'll witness that berm feature, but as we go through the winter months, you'll notice a lot less sediment on the beach. You'll notice the shoreline has retreated, and it looks far more bare. You'll also see that the beach in winter looks far more planar. See the creation of the bars there. Tide exerts a control on how the beach looks. In a macrotidal environment, where the tide range, so low tide to high tide, is greater than 4 metres, you get a sweeping zone of tidal concentration. And what that means is the tide is never focused at a certain point on the beach for a long amount of time. Because as it rises, all of a sudden the waves are acting on a totally different level of the beach. And we'll look at that in a moment. So as I said, the wave energy is only focused on a small area. And we can imagine that here. So we've got the beach face and the berm, and we can see a high and a low tide level marked. Now imagine there's 6 hours between that high and low tide. You can start to divide that up into sixths, and you can see that for an hour, the tide is focused on a relatively wide area compared to in the moment when we look at meso or microtidal areas. And we can talk about tidal translation. Tidal translation is how far the tide goes up the beach in terms of x coordinates as opposed to height, compared to how long that takes. So tidal translation is how far it moves up the beach over time. If we compare that to a microtidal environment, where we still have 6 hours between the high tide and the low tide, you can see that the tide spends, or the waves are kept at a certain level, and they act on a smaller area of the beach for a longer amount of time. I've already told you that the waves are responsible for, or certainly swash is responsible for the creation of a berm feature. So straight away we can start to see that with the waves acting on a smaller area for a longer amount of time, that microtidal environments are more conducive to formation of berms. Because the waves act in one place for a lot longer. And here we see a low tidal translation rate. I.e. it's not travelled very far, but the amount of time has been the same, so that ratio between distance and time is a lot lower. Okay, here's an example of a couple of those beaches then. The picture you see is Perranporth. It has a high tide range, 6 to 8 metres at times. And what that means is the shoreline changes rapidly. It sweeps across the entire beach. The width of this beach, between high and low tide, is somewhere in the region of 600 or 700 metres. Okay, that's how far the tide moves in and out. Compared to some, for example, Australian beaches, microtidal, where that distance between the high tide mark and the low tide mark can be on the order of 20, 30 metres. Okay? So the UK is predominantly macrotidal, places like Australia are predominantly microtidal. So what you don't see at Perranporth is berm features, because the tide range is too high, the waves aren't concentrated in one place for long enough to build up such a feature. So they are flat and largely featureless because of that large intertidal zone, that high tidal translation rate. When we go to microtidal then, straight away you can see a much steeper beach. You can see the top of the beach, just along here, and you can notice that there's maybe 100 metres, 150 metres between the two areas that you can see. Straight away we look here and we see that we get bar and berm features because of that wave focusing on a smaller area for a longer amount of time. So as opposed to just sediment size being controlled on steepness, gravel versus sand, we also see tidal height or tidal regime is also a control. When we look at wave breaking then, you haven't had the waves lecture yet, so I'm going to introduce you to a breaking criterion. What this is a way that we can predict in what water depth waves will break. And that has massive implications for coastal planners who want to know whether their beach is going to erode, they want to know how high their sea defences need to be. And the way we do it, we predict that wave breaking height, the capital HB, with a breaking criterion compared to the mean water depth. So the first thing we're going to do is take the water depth we're interested in. So if I have 1 metre of water, and I want to know what size wave will break in that 1 metre of water, I can take this criterion, which here is 0.78, so it's about 0.8, times the two together, and straight away I can see that in 1 metre of water, a wave that is 0.8 metres high will break. Okay? That value changes. That's the standard value that you'll see quoted. It changes depending on sediment size, it changes depending on tidal range, etc., etc. So you can look into various different studies which will give you different estimates, but as a good starting point, 0.8 is a rough estimate. And you can see that here, although it's not really to scale. We see what we spoke about earlier. We get offshore, nice circular orbits. You then get the wave interacting with the seabed. The bottom slows down, the top carries on moving forward, the wave becomes unstable, and we go into a regime whereby the top is toppling forwards and we're inducing breaking. So we've gone from deep water into the shoaling zone and into the surf zone. The surf zone, as I said, being where those waves break. They break in a number of ways, and we're going to introduce you to those now. The first type of wave breaker is a spilling breaker, and this happens on gentle beach gradients. So the scenario I gave you earlier was there was a submerged offshore bar that induced a massive change in depth that the waves couldn't cope with. So really quickly, they toppled over and broke. On a very gentle beach, that change in depth is so gradual that actually the top of the wave slows down at a similar rate to the bottom of the wave. So we get what we call a spilling breaker. Okay, it happens on either gentle beach gradients or when the waves are steep. We see a gradual peaking of the crest as opposed to that rapid spillover until we get to a point of instability, and then rather than crashing down, the crest of the wave just spills forward. And that looks something like this. Okay? So we don't see that dramatic crashing where all the surf pictures going through the tunnel or the tube. We get a much more gradual break on the beach as a result of this low gradient. That compares to a plunging breaker. Now this is where the top crashes over in slightly more spectacular fashion. It happens on steeper beach gradients or slightly lower steepness waves. The shoreward face of that wave now does become vertical, at which point the top curls over, as opposed to the spilling breaker, where we never get the wave at a vertical point. It's always moving forward with a forward angled face. It plunges forward as an intact mass of water. Okay, so it doesn't break up as it topples. And that looks something similar to this. And you can see they've tried to depict it here with as it curls over, it's still one mass of water. Even though there's that hole in the middle, it's one mass of water all the way over until it impacts the seafloor. So that we term a plunging breaker. If we go to really steep beaches or low steepness waves, we get what we call a surging breaker. And this is effectively where the wave doesn't really break. So the front face and the crest remains smooth and intact. It slides directly up the beach without breaking. And the reason it does that is because, quite simply, A, there isn't time, there's too rapid a transition in depth, but B, the waves aren't steep enough. So imagine a nice long wave where you've got a very shallow crest as opposed to a steep wave. As it surges up this shore face, the top doesn't topple over, so you just get a transfer of energy up the beach and back down. So the three types of breaking wave: spilling, plunging, and surging. And they correlate to increasing wave steepness. Now we can predict how they're going to break based on a number of parameters. Okay? We call this the Iribarren number. And if you do any further work on beaches and on beach erosion, this Iribarren number becomes key. It's dimensionless in that it doesn't have units. Okay? It's just a number. And it looks something similar to this. Okay? You do need to know this one, so please do at least understand how to compute this, as it will feature later in the year. The first thing we take is tan beta. Now, tan beta is the gradient of the beach. It's important to note that's not the tangent of beta. Tan beta is the term itself. Okay, so don't try and take the tangent of the beach gradient. And the other factors that we feature into it are the breaking wave height and the wavelength in deep water. When you do Ivan's wave lecture, you'll see how waves change from deep water to shallow water. But it's important to note that for this Iribarren number, we're interested in the deep water wavelength. So if we take a look at what that translates as, if we get small values of the Iribarren number, less than 0.4, we can predict that the waves breaking at that location at that time, based on the parameters you fed into the equation, will be stilling. 0.4 to 1, we can predict they are plunging. Anything over 1, we predict are surging waves. And that links back then to the steepness. Okay, you can see how the wave height over the deep water wavelength will affect the number that comes out the bottom. Everything I've said about wave steepness now features into this and allows us to predict those values. What I want you to do, if you've got a calculator, great, use it. If not, you've got laptops or phones, whatever you want to do, take a couple of moments to calculate the Iribarren number for that scenario. As I said, there's no one feature in the exam, so please have a go at it yourselves. If you can't work out how to plug those numbers in, if it doesn't come out with a sensible number, i.e. something between 0 and 2, then give me a shout, I'll come and have a look, and in a few moments we'll talk through how we go about calculating this. Okay, let's talk through how we've gone about calculating that then. First of all, what goes on the top of the equation? What value? Yeah, good, 0.15. Again, remember the tan beta is the value itself, not the tangent of 0.15. Top left then, what goes there? Good, 1.4, and obviously that leaves us with A. What values did you get out? Any ideas? 0.3, 0.35, good, okay, 0.36. So what does that give you in terms of a breaking wave? Yeah, good, okay, it's a shallow gradient and therefore we get a spilling wave, okay. Those waves have different controls on beach. A spilling wave is predominantly onshore motion and energy. There's no great braking that entrains sediment. If sediment's not entrained, you can't then take it back offshore with the backwash. So it's predominantly an accreting wave. It has most contact with the seabed whilst it's moving onshore. Plunging suspends most sediment. You can imagine the front of this plunging wave is almost like a bore down onto the beach, and that mixes up all manner of sediments. Okay. Whether a plunging wave erodes or accretes is dependent on other factors, such as the overall wave height, etc., etc. But what we need to know is that it suspends most sediment. But we can't really work out whether it's going to accrete or erode overall without a bit more information. But what we do know is that a surging wave is most likely to erode the beach. Okay, it has very little contact with the offshore because all of a sudden it's shoaled, it's got into shallow water, so all of its contact is with the beach itself. So the only sediment a surging wave can train is sediment on the beach itself. And therefore the only place that sediment can go is offshore, as opposed to waves here that are starting to impact the seabed a bit further offshore and can bring sediment onshore. Okay, at that point we're going to take a 10-minute break. We'll start again at 10 to, by all means go grab a coffee, etc. if need. Okay, and we'll make a start there again then. What we're going to look at now is the nearshore currents that influence the beach. We're going to start with the longshore current. If you've studied this before, your understanding of the longshore current is probably that particles move up the beach at an angle, back down, up the beach at an angle, back down, etc., etc., in a seesaw motion. That does move sediment alongshore, but it's not the primary means of a longshore sediment transport. Most of the sediment isn't moved on the beach. Okay, and we'll look at that now. So it's dominated by surf zone transport as opposed to swash zone transport, which is what you would have been taught at GCSE or A-level geography. Flows are generally in excess of a metre per second, okay, in the surf zone. Those flows increase with increased current as wave energy increases, and they also increase as that incidence angle increases. So we can look at that now. We have some wave crests that aren't shore parallel, okay, in the surf zone. And what you see is that drives now longshore sediment transport. The majority of that sediment, as you can see, is moving in the middle of the surf zone. It peters off outside the surf zone. We get some sediment transport in the shoaling zone, and likewise swash processes here would drive a degree of a longshore sediment transport, but nothing comparable to what happens in the surf zone itself. As we change the angle of those wave crests to orientate them even further along shore, you can see that sediment transport exponentially grows. Okay? i.e. the middle grows even more, and we see a slight increase on each of the tails as well. So the main take-home message here is that in terms of the alongshore current, it dominates in the middle of the surf zone. What I want to look at now is bed return flow. So as waves break onto the beach, bed return flow is the second type of current. This is an offshore directed near bed flow. It's part of a vertically segregated circulation pattern. And what I mean by that is if you split the water column in two, on the top you have onshore transport through waves, on the bottom you have offshore transport as a result of bed return flow. These are much smaller velocities than the alongshore current, and they're smaller because they're gravity driven. So they're generally 0.1 to 0.3 metres a second, but that depends on the gradient of the beach itself. So a steeper gradient beach, that gravity is going to have more of an effect on the bed return flow. We're going to see greater velocities in terms of bed return flow. So you can see in the diagram we have onshore mass transport in the waves. That's the wave crests breaking forwards. All of that water that piles up on the beach has to go somewhere. And as it comes back down, we see at depth a return flow along the seabed beneath the waves. That's the flow we're on about, those offshore directed arrows at the bottom. Okay. And that's the vertically segregated circulation that we spoke about. A net onshore transport at height, a net offshore transport at depth. You can see again, the flow is not maximum on the bed itself. It's maximum a few centimetres above. And what we're going to look at now is the third type of nearshore current, and this is rip currents. So these are strong, narrow, offshore directed currents. Okay, if you've been on the beach, you've suddenly experienced the fact that you're out of your depth and you're being moved offshore. That's the rip current, that offshore directed flow. Rip currents are responsible for about 70% of lifeguard incidents on beaches in the UK. So they're a huge, huge problem when it comes to recreation. Generally, they're about 0.8 to a metre per second. Okay, so straight away, just at that lower end speed, a metre a second, you can see that in 2 minutes, a rip current could potentially have moved you more than 100 metres offshore. And that's why they're dangerous. However, in some conditions they can reach 2 metres a second. Okay? So now, in a minute, you're 200 metres offshore. As I said, they are a significant coastal hazard. If you can see at the top, I've given you 70% in the UK, 80% of rescues in Florida involve, 80% worldwide. In Florida, they cause more deaths than lightning, hurricanes and tornadoes combined. Okay? Because, whereas lightnings, hurricanes and tornadoes strike every now and again and take a fair few lives, rip currents are there constantly. Okay? Day in, day out. And the attrition rate is huge. What you can see in this picture is a whole mass of people caught in a rip current. Okay, a few minutes ago they were bathing happily along here, but what you can see is a rip current is fired up, and this is one that was a result of wave forcing. So a certain wave group has come in, it's created the conditions for that rip current, and all of a sudden you've got large offshore flows. And you can see a number of rescue boats coming in to try and help people. This situation, it's in South Korea. It's exacerbated by the fact that a lot of these people were in rubber rings. So yes, they're not going to drown, but because they're in rubber rings, their feet aren't in contact with the floor, and therefore there's nothing to oppose that current offshore. So they're just floating in the current and taken a large distance offshore. If we look at this picture, or this scene a few moments later, where they've totally cleared the area that was at risk, you can see that actually, yes, you might see a slight offshore tinge in the breaking waves, but you don't really see any real hazard. Certainly if you were just stood in the water, you wouldn't have this nice overview that we have to be able to see that there was a hazard there. And again, that's what makes them dangerous. You can spot rip currents because they look like the calmer areas of water. And the reason they look like calmer areas of water is because generally they're driven by channels. Channels are deeper, and therefore there's no wave breaking. So what you'll see is white water where the waves are breaking either side, and in the gap you'll see an area of darker water. That's the rip current. And because it looks darker, because there's no wave breaking, people think that's safer, they go to there to swim, and ultimately they end up taken offshore. So we'll look at how a typical rip current forms. Okay? Typical is in quotations because it changes depending on wave conditions, tide, morphology, etc., etc. But what we see here is the shoreline, and offshore we have some form of offshore irregularity. So in this case, picture that as an offshore bar. We get an onshore flow in terms of shoaling waves. They reach the bar and they break over the bar. So you've now got mountains of water, not mountains, you've got a huge amount of water piling up behind the bar, up onto the beach. It can't return because that bar is keeping it onshore. So it moves along shore and it looks for a place to exit. Now this might be a gap in the bar, it might be a weakness in the bar, but ultimately it will find somewhere or some place whereby it can return offshore. And at this point, you get all of that water from a wide surf, so typically 200 metres wide perhaps, going offshore in a 20 or 30 or a 40 metre channel. That's where you get the fast offshore flows. Okay, and as we get to the end, you get the rip head where all of a sudden we're now outside the breaking wave region, and that rip current starts to disperse. Sometimes what you find is that rip currents operate in cells. So you can go out on the rip current, but then it will circulate back in on the breaking waves, and it'll go round and round and round, unless you can swim out of it. Okay? So that's the basic premise of how rip currents operate. Now, I've said that's a typical rip current system. It doesn't often happen like that. But what I want you to do now is take a look at this picture. This is an aerial photograph of a time when it did happen like that. What you can see is obviously the beach down here. You have breaking waves over the bar. And what's happened is this is a rip current experiment. And to track that rip current, someone's put dye in the water down here. And you can see really nicely that it tracks along shore. It suddenly finds a gap in the bar. Notice there's no wave breaking there, but you get wave breaking either side. So there's a gap in the bar, the current has gone offshore, and it starts to disperse in the rip head. In this case, we're talking about a small scale. That's maybe 100 metres at most. Okay, but as I said, these can go 200 metres, 300 metres offshore. And if you don't get out of the current as it's taking you offshore, ultimately you end up that far offshore. Okay, moving beyond the three types of nearshore current then, we're now going to look at different beach types. Okay, there are a whole range of processes that operate on the beach and control the beach that you see. And the actual form of the beach at any time depends on the measure of these processes. So do waves influence the beach more than tides at a particular time, etc., etc. And what we can do is classify the beach in a number of ways. One way is a combination of the tide range. Now I told you earlier the tide range is important because a high tide range means that we don't focus energy on small areas of beach and therefore we can't build features. And that's what you see here. At the higher tide ranges, or the high tide factors, you see largely featureless beaches. Okay? But we also have a measure of fall velocity. So this is intricately linked to sediment size. So on the left, we have a low fall velocity, and on the right, we have a higher fall velocity. And you can see as we move across the classification, we go from steeper to slightly shallower. We also see that there are more features on the top than there are in the bottom. If we go beyond this tide range, you see a transition to tide-dominated tidal zones. And when Ivan covers estuaries with you, that's the sort of environment that you'll look at then. that's one way of classifying beaches. But we can also look at the morphology on the beach itself. Okay? And what you need to be able to do is recognise some of these different types of morphology. So we're looking at barriers now. I've already said the barrier is the longer term sediment accumulation. They are elongated. They are almost always wave orientated as opposed to current orientated. So wave dominated as opposed to longshore processes. So they're shore parallel, sand or gravel, and they are above sea level, i.e. they are very rarely impacted by what's going on in terms of tides and waves. And generally, barriers will have some form of back barrier environment. That picture I showed you at the start in terms of that unique habitat, that was a back barrier freshwater lagoon. And here it is again. Okay, so you've got the barrier along here. On the very front, you've got the beach, but what you can see on the back of the barrier is that there's buildings, okay, there's grassland or marshland, and there's some form of sediment on the back. So generally, the barrier isn't influenced by waves and tides, else you wouldn't have this grassland growing, you certainly wouldn't have built on it. But what is influenced is the front of that, the beach itself. So we're going to look at coastal alignment, certainly of barriers, and this is what I've just touched on. We get swash aligned, which is the dominant form of barrier, and slightly less often we get drift aligned. Okay? If there is a huge component of a longshore transport, you're obviously going to get a drift aligned coast. However, if you get diffraction of waves and the wave crests are parallel to the beach, as you see here, then you get a swash aligned coast. Okay? This is the differentiator, it's how the wave crests reach the coast. So you've got refraction around the coast here to get shore parallel waves, whereas here you don't get that refraction. There's not that dominant headland, and therefore the wave crests are approaching at an angle. And what that does is drive the barrier across the opening in a drift aligned manner. So let's look at how that's formed. First of all, the wave crest I've touched on. Parallel versus oblique. And now we can look at sediment transport. A swash-aligned barrier will be closed in terms of its sediment transport, i.e. here you will get onshore and offshore sediment transport, but it won't bend around the headlands. So that's a closed cell in terms of sediment transport. Whereas here, these wave crests are going to drive a strong alongshore current, and once we get to the end of the barrier, the sediment is going to carry on going. It's not going to form a barrier because there's not yet enough of it, but it's going to carry on going, probably around the headland, and disappear down the coast. So a drift-aligned barrier has an open cell in terms of sediment transport. Therefore, in terms of net literal drift, i.e. the addition versus the removal, this is zero. No sediment leaves this system. Whereas on a drift-aligned coast, you can see a positive or negative balance in the net literal drift. Okay, because we might get more sediment coming in around this headland, or we might get more sediment moving out, leaving us that positive or negative. So let's look at some swash-aligned coasts. This is again that picture that I showed you. So here you can see that freshwater lagoon. It's part of a massive bay. So this is Start Bay in South Devon. Up here you've got Dartmouth. And all of the beaches in this bay are swash-aligned. Okay? At high tide they become distinct beaches, but what you can see is there's a headland there. At low tide sometimes there's sediment that goes around the front of that and links those beaches. That is largely a closed sediment cell. No sediment moves in from around this headland, and no sediment is lost up here. Occasionally, we get riverine inputs, okay, but actually, largely, this is a closed sediment cell. Sediment can move offshore in storms, but it comes back onshore before moving outside. So you've got, as I said, Start Point and the River Dart. Here, though, we have a drift-aligned coast. Okay, this is Hurst Spit And what you see is the waves here propagate from the west along this coastline. They drive in a longshore transport, and that's why you get this entire feature here. Okay, that backland never used to be there. That sort of freshwater or mixed water brackish environment never used to be there. But as the sediment got to the end here, it had nowhere else to go, so it started to build a barrier along the shore. Okay. So we see that it's an open littoral cell. It's built this barrier, but when it gets to the end, it's got nowhere else to go, so it can wash around the coastland. So we get an input and an output, so it's an open cell. And that net littoral drift is unbalanced. And what that means is at the moment, what we've seen is a positive input. More has come in than has left, which is why we get the creation of this feature here. The combination of these processes can form interesting features. What we have here is a coast, and offshore some rocky platform. Okay? And the way the waves break around this rocky, not headland, but this rocky platform has influenced what's happening behind. So we see wave diffraction. Diffraction is in bold because in your lecture notes I think it says refraction, which is incorrect, so please correct it. Diffraction around that platform has formed a tombolo. And what a tombolo is an accumulation of sediment that's swash-aligned, that's reached out from the headland or out from the coastline towards this rocky area. So diffraction around, the wave crests propagate like so. We see an accumulation of sediment and it builds up and it builds up and it builds up. And you can see that it's been happening for so long that the back beach environment, or the back barrier environment, has been colonised by vegetation. Okay, so over long-term periods, that's now a stable environment. So tombolo, that's the first thing we need you to recognise. It can form behind offshore breakwaters. So what you see here is a beach that they wanted to protect, so they put some almost groins in either side, and to stop high energy waves eroding that beach, they put 3 offshore breakwaters in. And what they're seeing now is not only have they protected this beach, but the diffraction around those breakwaters means the beach is building out. Okay, eventually it will join up to all 3 of them, and you can see now almost cusps as those tombolos form between the beach and the breakwater. We looked a moment at drift-aligned barriers. We can get all manner of drift-aligned spits. Okay, and I'm sure you will have done this to death in any geography lesson, so we won't go into too much. But what I want you to look at is Dungeness. This chunk of the coastline never used to be there. This is all a result of a longshore sediment transport. So you can see it's built out and built out and built out. It's been colonised by vegetation, and up here you can see small squares where it's been there for so long they're now established into farmland. Okay? And they are, for all intents and purposes, long ago reclaimed land. And it's used just as any other part of the natural shoreline. And in the diagram up here you can see some lines, how that shoreline is prograded. We now get sediment transport that goes along here, building it out further. The wave direction changes slightly, and it moves up around the coast. Talking of that back barrier environment then. Again, we've got a barrier, we've got the beach on the front, and we have a number of options in terms of what can happen behind that barrier. First of all, generally, for there to be a back barrier environment, we will see some form of exchange. Now here, we've got a tidal inlet, okay, that floods and drains, or floods and ebbs as the tide rises and falls. What that does is deposit sediment on the inside. We have a flood delta, or flood deposition, and we have an ebb delta, or ebb deposition. So sediment is constantly moving through that channel. If this was entirely connected, what you would still see is a seepage through the barrier. So salt water would seep through the barrier into the fresh lagoon. Likewise, fresh water would seep through the barrier out into the beach. Sometimes those beach sediments sediments under high storms can wash over. So we see sediment deposited from the beach, taken over the back of the barrier, and deposited in the back barrier environment. Now that can happen not just under high storms, but also under rising sea levels. As the sea level rises, we'll see in a moment that wave action is concentrated higher and higher up the beach, and ultimately what it does is throw sediment over the back, and we'll see the barrier move backwards as a result. You see some sort of river input here. You can also see tidal flats. So now, tide range and the going and coming of the tide is the dominating factor controlling how this environment looks, not the waves, because all of the waves are stopped or certainly attenuated by this barrier environment. So now we get tidal deposition as opposed to wave deposition on the beach. And you can see on the back of the beach there is some aeolian morphology in terms of dunes. Now barriers generally form under stable sea level, so a changing sea level will not form a barrier. And again, this comes to concentration of waves and tides on one elevation of the beach. We need concentration at one elevation over long periods of time to build up significant sediment to become a stable environment. So they only form under stable sea levels, but they move under rising and falling sea levels. What we see here is a diagram of barrier, okay, in present day, and you can see under past sea levels, when sea levels were much lower, 100, 120 metres, the barrier was further offshore. Okay? As sea levels rose, it was moved onshore. And what you can see is that at this point it was stable for a while, because there's evidence, in terms of estuarine muds, of a back barrier environment. Those estuarine muds wouldn't have been there, wouldn't have formed there, if the sea level wasn't stable at that position for a long period of time. But it's moved back, and then you start to see the erosion of those features into the offshore. If we look at the present day, knowing that this has moved here under rising sea levels, what you'll generally see is again those estuarine muds underneath the front of the barrier, because this used to be the estuary when the barrier was here. Okay? And that estuarine deposition doesn't get picked up until it's eventually eroded by waves. This here is a beach again in South Devon, and what you're looking at is ancient tree stumps. From when sea levels were lower, the barrier was further offshore, this was a back barrier environment where marshland, trees, lagoons did well and thrived. But the barriers moved back beyond this, and now you're seeing this erosion at the front of the barrier, and things like this are exposed. So this is your example of the relic back barrier environment coming through onto the beach. One way that barrier can move backwards is a process called overwash. Okay? And this is where large storm events move the barrier landward. What you see here is an experiment in the Netherlands. They have a long wave flume, and all they've looked to do is track how higher sea levels and higher waves can move the sediment. And this is what they've found. So we get the water coming up, the waves break on top of the barrier, and they don't just stop and go back down the front of the barrier, they wash over and they carry all manner of sediment down the back of the barrier. So we go from a before profile, where we had a nice steep prominent barrier, to an after profile where all of this sediment has been taken over the back by the waves and deposited. And now the crest of the barrier that used to be here is now here, so we have a net onshore movement of the barrier as a result of overwash. This is again that first place that I showed you in South Devon, Start Bay. I showed you there was vegetation behind it, and also construction, also a village behind the barrier. Again, in those 2014 storms, what they found was that the front of this barrier, the beach, overwashed in such a way that it covered a road that runs from start point that we saw at the bottom up towards the River Dart. Okay, and again you can see another example of that overwash there. Now we've put a road in the way, so we're not allowing the barrier to naturally move. It's not naturally overwashing as it should, because without that road, what you'd see is that sediment's washed over, and then this becomes the new part of the barrier. But instead what they've done is clear it all away and deposit it back on the beach. So this is an example of man fighting against sea level rise, because this never used to have, this wouldn't have happened years and years ago, but we now have higher sea levels, therefore that wave action, those storms are hitting higher up the beach, and we're stopping the barrier from naturally moving landward as it's trying to. Incidentally, there is a massive consultation on this road in terms of how long they can realistically, given predicted sea level rises at the moment, we're looking at perhaps a metre sea level rise by 2100. Under those conditions, how long they can realistically keep this road here. Their other option is to route it around the back of that lagoon that I showed you, and that's a debate going on at the moment, because they know that they cannot keep clearing it whenever these events happen, because they're going to become more and more frequent under the rising sea levels. So overwash is the first process we're going to look at. Under rising sea levels, then, I've shown you that ultimately the shoreline retreats. What we're going to look at now is the Broun rule. Now, the Broun rule is a way of predicting coastal retreat. And again, this is another equation that you need to know for exams later in the year. This is derived by assuming that erosion in the upper part of the profile is balanced by deposition of the lower part. So there's no net loss or gain of sediment transport under rising sea levels. It's the most widely quoted and used approach to predicting effects of sea level rise on sandy coasts. It doesn't work for gravel barriers, it doesn't work for rocky coasts, but for sandy environments it's the most widely quoted measure of retreat. And what we can see here are the factors that influence it. So our R value is the total retreat that we see. So we can see the lighter brown is where the coastline used to be, and the darker brown is where this erosion takes place, or takes us back to under rising sea levels. And what you can see is that all the sediment we've lost here, we've effectively gained here. So there is no net loss or gain of sediment. The system has retained the same mass as it did at the start. The features that influence it then, first of all, the height of the subaerial beach. So we take the initial sea level and we look at how high the berm is before sea level rise starts to take effect. We then look at how much sea level is going to rise. So this S value is the change in sea level. And finally, we look at the depth of closure. Okay? Because this gives us an idea of how far offshore, or at least how steep the profile is, before waves are starting to influence the seabed. And we can plug that all into the equation that you see there. That L value, is the length of the shore face. So that's depth of closure to the shoreline, as we see there. We've got a minus value in the equation because we're predicting a shore level retreat, so that negative value gives you the distance. What I want you to do, same again then, calculate the shoreline retreat in the scenario that you're given there. Again, a couple of minutes and then we'll discuss it and go through the answers. Okay, good. Right, let's take a look at what we can plug in. So first of all, minus value. Anyone pull it out? Good, -1, so that's our sea level rise. What we're going to see on top of the equation. Good. Okay, on the left of the equation, then at the bottom. Good. Leaving us with 3. What value did you get out the back end of the equation? Okay, yeah, good. Okay, we get a shoreline retreat of just shy of 30 metres. And that's only with a metre rise in sea level. Okay, so admittedly for 2100, a metre is about the worst case scenario that we're predicting. But on sandy beaches, that means that there's a 30-metre lateral retreat. If you now think back to that barrier I showed you a moment ago, the width of the beach wasn't even 30 metres before we got to the road. Okay, so under a metre of sea level rise, there is no way that we can sustain barriers such as that by artificially holding them where they are. We need to ultimately let barriers such as that go with the sea level, wash over, and reduce that back barrier environment. So under sea level rise then, we say the barrier retrogrades, i.e. it moves onshore. And we can predict that with the Broom rule. There's a couple of ways that the barrier can move onshore. The first is translation or rollover. And what we see here is exactly that overwash process that we saw, where the top of the barrier is chucked over the back, the beach face then erodes, and that's chucked over the back. And all we see is a constant overturning of sediment as the barrier moves onshore under rising sea levels. We can see overstepping. This is where sea level rise is too rapid for the barrier to keep up, in which case it becomes abandoned. So here we had a small sea level rise. The barrier could keep up with that just by rolling backwards, but here sea level rise was too sharp for the barrier to keep up, so it's been abandoned. And now, over time, we will get a gentle erosion of that sediment onshore and a new barrier forming. So in an overstepping scenario, you have two barriers coexisting, one of which is submerged. In a translation or a rollover scenario, we get the one barrier that slowly moves onshore. Okay, such as, to a certain extent you can see here, this is a bit misleading in that this was the result of tsunami, but what you can see is a massive overwash. So here you used to have the beach and the road, and then just grassland and houses behind. But as a result of a higher sea level, an elevated sea level, massive waves, you see an overwash, which has spilled into the back of the back barrier environment. And likewise here, this isn't the result of a tsunami, this is rising sea levels. You can see that the beach here has started to be eroded and it's been breached. So this used to be one long straight coastline, but now we see holes appearing because that rising sea level is causing erosion. We're throwing sediment over the back, and that barrier will start to roll over or translate. Under sea level fall, then, we say the barrier progrades. And this is the creation of a strand plane under a positive sediment budget. Okay? So what that means is the barrier is left up high as the water moves down. Under a negative sediment budget, we're not quite sure how that would affect the barrier itself, just based on only that information. So what we see here is we used to have a barrier environment here. Sea level has fallen, and as it goes, it takes some sediment with it. But because it's falling, it can never fully erode that sediment at the highest elevation of the barrier. So now we see ridges all the way down the strand plane into this new, current barrier environment. So it will take some sediment with it, but ultimately, overall, it will probably lose sediment, because this sediment is now no longer worked by wave action. So that's what we mean by a strand plane, this rippled surface down to the current day sea level. And finally, what we're going to look at is just the various responses. Okay? You should have all the answers to these in your sheets, so I'm not going to ask you to guess them. But under a falling sea level and a positive sediment budget, i.e. the sea level is falling away from the old barrier, therefore it doesn't need that sediment, or it won't use that sediment. Under a positive sediment budget, we're still going to build a new barrier, we're still going to prograde the barrier. Likewise, under a neutral sediment budget, we can still prograde a barrier based on the old sediment. And if the sea level is stationary with a positive sediment budget, again we're going to build the barrier in its current location. If we have stationary sea level and no new sediment coming into the system, no sediment loss, then the barrier is going to stay as it is. However, if we go to a rising sea level with negative sediment or neutral sediment, we're going to see that barrier moving onshore, that retrograding barrier. And finally, a couple of situations where we don't really know what's going to happen. So a rising sea level and positive sediment budget. Is that new sediment into the system just automatically going to go over the back of the barrier and build a new barrier? Or are we going to take all the sediment from the old barrier onshore? And likewise a similar situation with falling sea levels and a negative sediment budget. We don't really know. It's all case by case. There's not an overall answer. In summary then, we've looked at beaches and how they are primarily controlled by wave processes. We've looked at what those controls are. So we've looked at how tidal translation and different wave steepnesses influence how the beach looks. And we've looked at temporal responses, such as that seasonal cycle of summer or calm conditions, where we get firm on shore, compared to those winter or storm conditions, where we see erosion and the formation of offshore bars. We've looked at the three main nearshore currents, so bed return flow, longshore current, and the rip currents. And again, my main take-home message on that is that longshore current primarily operates in the surf zone, not on the beach. And we've also looked at barriers, their alignment, okay, depending on the oblique waves or the angle the waves reach the coastline. We've looked at how barriers can respond to sea levels. And to summarise all of these, if you're going to go further with coastal type things through the course of your degree, certainly if you're thinking your dissertation should be on something coastal, I really recommend the book on the left. I used that through my undergrad and my master's, and I'm still using it now. If you want a bit more of a technical insight into some of these processes, so a bit more understanding of how those equations we've covered come into play and various different values you can use for them, then the book on the right is the one to go for. Are there any questions on any of the content?